Good evening, everyone, and welcome to the last edition of our seminar this semester. Welcome to today's edition. Today we have two interesting talks. First, about structural tube design for AlphaTube by Oliver Wach, and the second talk is from Joe Holler, and it's about rapid pipe segment installation regarding time and cost optimization. Now I'd like to hand over to Fabio for a short announcement, and then we start with the talks.
So thank you very much, Natalie. Looking forward to the last seminar. Only if you can go to the next slide. Just want to give a quick announcement for the people that might get bored over summer or want to join a nice project. We are currently opening some positions at the EuroTube Foundation. We're having positions for junior engineer, scientists, and analysts. So we have a large variety of open positions that you can apply for. Please send me your application until the 14th of June so that we can start a possible discussion to get to know each other. This will include a short motivation, just some sentences, your CV, and if available, a project portfolio. We would be very appreciating if you would be applying for such a position with us to shape the future of sustainable transport. Yes, here you also see some exemplary projects from electrical, mechanical, engineering over to business analytics and also network studies. Yes, happy to receive your applications and get to know you. So now I think, Natalie, you can explain again the Slido, and then Oli, I'm looking forward to hear your results.
Yes, as every week we use slido.com for the questions, so you can take either your web browser or your cell phone. You can go to slido.com, then you can enter the event code, which is WEC Transport Seminar. And then during the presentations, you can type in all your questions, or you can see the other questions that other participants already post, and then you can upvote those questions. And after every presentation, we have a short discussion all together, and we go through all those questions that the speaker then can answer. Okay, so please join us and go to slido.com. The event code is WEC Transport Seminar, and then we can collect all the questions. And now we'd like to hand over to Oliver Wach, and we look forward to your presentation.
Okay, thank you very much. So I also welcome you to this seminar of Swissloop. And my name is Oliver Wach. I am a master's student at ETH at the Department of Baustatik and Konstruktion, IBK. And I am doing my master's thesis about the structural design of the AlphaTube project for EuroTube. Short about the content of this presentation, I will first go into the problem statement of my master's thesis briefly, and then I will share with you my variation study, which I did before I chose a system for the structural design of the tube. And then we will briefly discuss the conclusions from the static analysis of my proposed design before we go into the questions. So as I already mentioned, I am working for EuroTube, which is a Swiss non-profit foundation in Zurich. It's working on its first project, the AlphaTube, which is actually a Hyperloop that shall be situated in the Canton Wallis and that shall provide a testing facility for high-speed vacuum transportation. So the goal is to construct this tube either in steel or in concrete so that vehicles move with a maximum speed of 900 kilometers per hour through this tube. And my master's thesis task is to do a variation study, so in the conceptual design phase, and choose the best or the most convincing concept of these for structural design and show that it's feasible. So when I started this master thesis, I first had to identify the boundary conditions and the performance objectives of this task. And I started with collecting the boundary conditions, and the most decisive ones are listed here on the left side. So first, the tube is about 3 kilometers long. It's actually almost straight, so there are no curves. The tube is not monolithically 3 kilometers long, but it's divided into 20-meter long so-called sections. So actually, it's every time it's a simple beam. You can see this here on the right side. So a simple beam, for the ones who do not know what this means, it's a simply supported beam, which means that one side is fixed and the other side is a roller beam, so it can move. The average diameter of the tube is about 2.28 meters, and the shell thickness is only 8 centimeters. Just a brief input. This is very, very thin compared to usual structures in civil engineering. So it's a very innovative project. Then the performance objectives are most likely 2 of 3, which are very important. The first is that every 20-meter segment may not exceed 45 tons weight. Why is that so? It's just because otherwise the lifting vehicle, which transports the 20-meter segment to the site, is not able anymore to lift it. And the other performance objective is that the vehicle which goes through the tube may not experience a bigger or larger deflection than 2 millimeters. So the bump may not be more than 2 millimeters. That was the performance objective given by EuroTube at the beginning. And last but not least, the outer surface of the tube must be compatible with a liner. So the liner is here in the end to make sure that no air is going into the tube, because of course during operation there is a vacuum, or most likely not an ideal vacuum, but something pretty similar. So then I started to collect and identify the complexity of this problem, and I collected most likely 5 subcategories. So the first category is the cross-sectional setup. This means actually the layout of the pre-stressing elements, which are needed to pre-stress this tube. So in civil engineering, we very often use pre-stressing elements to counteract the vertical deflections which happen due to the self-weight. Yeah, most likely. So the cross-sectional setup indicates whether the pre-stressing elements are situated inside the shell or externally, which you can see in these 2 illustrations here. Then there is also the question at the second category, how to pre-stress the tube. There are in civil engineering most likely 2 categories to do, or 2 methods to do this. One method is to use so-called pre-tensioning. This means that you have some kind of 2 walls, and in between these 2 walls, you fix pre-stress elements and you stress them, and then you cast in between. And after the concrete has hardened enough, you just cut the pre-stress cables so that they induce over frictional forces the pre-stressing into the structure. The other method is the so-called post-tensioning method, and the post-tensioning is used especially for prefabricated concrete elements. So you can see this illustration here where you have 5 elements prefabricated of concrete, and you just align these, you pull a cable through all of these, and then you pre-stress it in the post term. The third subcategory was the segmentation. So the problem is that a 20-meter long tube can most likely not be cast in one piece, so not monolithically, because it would end up in very bad quality. So it's kind of a must that we segment the tube. The question is just, how do we segment it? The fourth point was the selection of the materials. So we have 3 main material choices to do. First, the composite matrix, which would be the concrete. Second, the active reinforcement, so the pre-stressing elements. And third, the passive reinforcement, so reinforcing steel bars, as we know it from construction industry. And last but not least, the whole system must also be feasible in terms of construction. So we must consider some construction concept which works in the end. So all these 5 subcategories led to this design strategy. You can see it here, this division, the setups, the pre-stressing, the segmentation, the materials, and the construction concept, just as we discussed it before. And now in every subcategory, you can choose one of the options. And if you choose from every subcategory one option, you have a so-called configuration. And the idea was to pick some configurations, check them on their feasibility, and if they fulfill all the performance objectives mentioned before. And if they do so, it's a possible solution. If not, we have to iterate and find a new configuration. And this is what got out. So this is my proposal, or at least one of 2 of my proposals for the construction. So if we look at this, this is the construction sequence, part 1 of 3. We start here by casting so-called tiles. So we call this system the tiling concept, because we have some kind of tile pieces which we put together. And so after they are cast, we place them. Either we just place 1, or we place 2 which are fixed together. And then we can lift from top the subtrack modules on these tiles, close them, and then align them. So this means that we have, let's say one of these modules is 2 meters long and the span is 20 meters. This means that we have 10 such modules. Why do we separate into these 2 module constructions? It's just because we want to avoid that we have cross joints. So when you see these longitudinal joints here, the goal is to avoid that the next module has also at the same height the longitudinal joint, because cross joints are known in construction industry to be weak spots. Then also the longitudinal joints, they require a certain fixation mechanism. And after some research, we saw probably something like this. So a V-shaped shear connector, which is pre-stressed, could be the solution, because during construction, there is no vacuum. And if there is no vacuum, the whole structure might fail in itself. So we have to make sure that the structure is stiff enough during construction. And this is why these V-shaped anchors should be used. Also, all the joints are filled with epoxy to make sure that the frictional forces can be transmitted. So after all these 10 modules are aligned, the pre-stressing occurs, which is indicated by these arrows here at the left and at the right. And when the tube is pre-stressed, we can just move in the rails, which are also 20 meters long. Then we apply the liner. The liner consists of 2 layers. One layer is here to ensure the vacuum, and the other layer is to protect the first layer. And then we transport this segment or this section to the site, place it on these gray pipe support elements, and at the end we only have to make sure that the joints are sealed. And for this we have to use some kind of a system that not only seals the joint, but also is deformable, because due to the self-weight, the sections, they will deform like this. So there will be a rotation at the supports, and this rotation must be taken by the deformation of this red joint here. So let's just briefly talk about the conclusions from my static analysis. I mean, I could show you about 1 hour my static calculations and everything, but this is way too complicated. So I just show you the principle, what we thought we could do. So before I start, I have to mention that concrete is a very, very tricky material because concrete over time loses stiffness due to shrinkage and creep. This means, for example, the E modulus drops to about a third of what its initial value was. So we have to consider somehow a system or some pre-cambering, so a measure where we uplift the subtrack at the beginning so that after time it can displace vertically and that the vehicle just experiences the difference of this displacement. So that's what we did here. So at the left you see the tube without displacement. This is the dark line, and the red line is the subtrack, which is leveled in such a way that it has an uplift in the midspan. And when you place it, that is the middle of this illustration, when you place it on site, then the tube will deform a little bit due to its initial weight. And the goal is that we have still an uplift of 2 millimeters at midspan when the vehicle goes through it. And then the idea was that after some time has occurred and all the long-term effects have passed, that the maximum displacement downwards experienced by the vehicle at midspan is still 2 millimeters. Unfortunately, I was not able to achieve this goal. 2 millimeter displacement is a very, very small tolerance. And I have to mention that in civil engineering, in such heavy constructions, the typical measures or tolerances are at the range of 10, minimum 5 millimeters. So this is due to the fact that there are many fluctuations also in terms of material parameters, such as the E modulus and whatsoever. And it's just not feasible to say it will only deflect 2 millimeters. A measure to still achieve the objective of 2 millimeter deflection is to use, for example, hydraulic presses below the modules, the subtrack modules, so that you can level the subtrack independent of the structure. This would be quite nice because then you could manage your system independent of the structure itself. And then the second conclusion, most important conclusion from my static analysis, was that these longitudinal joints, so these ones here, which are shifted every 2 meters, they are not so practical because I mean we discussed a lot about this and we thought it would be an advantage to do it like this, because then we could just lift the subtrack modules from above and we could use the economy of scales and do the same tile, I would say, I don't know, 50,000 times whatsoever. But the problem is all these connections, so these V-shaped pre-stressed shear connectors, they are also expensive. You have to install them. You have to close all the joints with epoxy. And in the end, most likely it would be more expensive due to the labor cost compared to a system where you just have 2 meter long tubes and you only would have the cuts in the longitudinal directions or the ring joints. And also EuroTube already successfully produced such about 2 meter long tubes, and the concrete quality was very nice. So it should not be a problem to change to such a system without these longitudinal joints. Yes, and I think I'm already at the end of my presentation. I hope I did not exceed the time spot, and I'm open for questions now. Thank you very much.
Okay, thank you, Oliver. It was very interesting. I think we go right to the questions from Slido, and if the audience still has questions, feel free to type them in. So the first question is, can you explain the average diameter of 2.28 meters? Where does the variation come from?
Yes, so the first strict objective I had was that the minimum inner diameter is 2.20 meters. And then you just increase the thickness of the shell until you reach the 45 tons limit. And with a thickness of 80 centimeters, you have exactly this average diameter. So you have the inner diameters of 2.2 meters and the outer diameters of 2.36 meters, and the average one is just from mid to mid of the shell.
Okay, then somebody would like to know if limits on maximum deflection is not possible and the joints are difficult to make, then is the alpha tube impossible to be built?
No, I think that's what I added to this statement, that probably if you use some kind of adaptable concept, for example, the hydraulic presses, you can still, independent of the concrete structure itself, level your rails, and then it's no problem anymore. So such a system should definitely be considered, especially because the subtrack modules are modules, so you can replace them if you want.
Okay, and the next question is, which tests would you perform to characterize the mechanical properties of the concrete, for example, as seen on slide 7?
So we already discussed with my assisting professor and my assistants about this. And because this project is so innovative, most likely you should 1-to-1 or maybe 1-to-2 scale test at ETH or maybe at EMPA, especially if you want to still keep these longitudinal joints. So these longitudinal joints, they are the reason for a lot of headaches, especially for my professor. And he would like to do tests of those. And if they are avoided, I think you can decrease the size of the test, maybe to 1-to-2.
Okay, and somebody would like to know, what is the preferred way of handling / gripping the tiles? What are the options?
Yes, in civil engineering, especially in geotechnics, so they're in tunneling, there are so-called grippers, something which works with suction, so with vacuum. So the grippers, they take these tiles and suck them and transport them. And this is a very common thing in tunneling. And I would propose that maybe you have some kind of a street, and in the street you have maybe 2 or 3 grippers, and you just hold them together until they are fixed in the joints. And I mean, also if you would avoid the longitudinal joints and you would just produce these 2-meter long tube modules, then you could also grip it with a hanging system or something like this, because then it's way less sensitive, the system.
Yeah. Okay, so we have 2 questions remaining and also 2 minutes remaining. So the next question is, what is the pre-stressing force on the cables for the 20-meter tube? How will you connect the pre-stressing across two different 20-meter sections?
Yeah, okay, that's a good question. So every pre-stressing element has 195 kilonewton. So it's 70% of the characteristic ultimate load. This is typical according to Swiss codes. And you do not connect the pre-stressing elements between 2 sections. You just pre-stress one section of 20 meters, you fix it, and then you decouple it. So you have the next section, which is also an individual pre-stressed structure. The only connection is actually this joint, the red one, which I showed you.
Mm-hmm. Okay, and the last question is, how much would a hydraulic support system increase the cost of building a track?
I don't know. This is a question I cannot answer. This is something we have to study after my thesis, because it's also not a civil engineering question, I guess.
Okay, so thank you very much, Oliver, for the interaction and answering the questions.
You're welcome.
For the presentation. Then we would like to hand over to Joe Holler for his talk, and we're looking forward to it. Thank you.
Good, perfect. Okay, can you hear me?
Yes, perfect.
Okay, thank you for the opportunity to explain a little bit the infrastructure and the idea how we should install the pipes cost and time optimized. My name is Holler. I worked 22 years in aviation, 13 years with Swiss Federal Railways, took responsibility for production railway technology, was always involved in innovation projects. That's the reason I came in contact with EuroTube, as SBB is sponsoring the steel rails for the tube system, beside other land utilization and project support. And it's fascinating, and it was one of the motivation after my retirement end of November to continue working for SBB. They also wanted to have me back, and I have the privilege to work on 5 innovation projects. One of them is supporting EuroTube. My presentation is to give you a glance at SBB infrastructure, to understand building a network is one thing, maintaining it is another thing, to give a little bit an idea about the dimension, what we have to respect in regard of pipe installation. We have a vision how we could do this, and we hope we get a lot of crazy inputs how we even can do it faster. SBB infrastructure runs 3 systems. One is the telecom system, the energy system, and the railway system. On the left side, you have the figures, impressive figures, and you have to calculate that every year you have to replace average 4% of the network because of damage and deterioration. This gives a lot of works. And the history of the network forces us to cover all technology, but also brand new technology. And in case of an incident, we have to work immediately to keep the network running. Just to give you a sample, if a train runs from Bern to Zurich, 200,000 switches have to function that the train will not stop. Switches, electronic devices, wheel counters, and so on. If one of them fails, we have a problem. As the trains run around the clock, we still have to fight to get access to the network. This leads most of the time to work during night for the regular maintenance, except big project where sometimes we are allowed to close down the line. We only work 11 o'clock in the night to 5:30 in the morning, or 4:30 if we are in the area of the Z5V, where the regional trains start early. Just to give you some figures, you see what we replace every year as sleepers, ballast. We also turn around roughly 850 kilometers of rails. They are imported. Switches, every switch is a customized switch. We don't have 2 equal switches, so we cannot produce them in advance. We have to produce them on demand. Leads also to 30 construction sites per day, and nice for the supply chain is normally after one night, they have moved to another place. So all marshalling of material, disposition of low-cost cranes, crews, material has to be adapted every night. Besides this is all normally work which is planned. Then we have the damages in the network where we have to act immediately. We have to be within 30 minutes at every point of the network, all the 3 networks. For the smaller things, they have material and tools with them. And then we have the heavy cases. One of the worst was Lucerne, where we have a derailment of the Cisalpino, and 5 switches got completely damaged. This happens 0 to 1 time, 4 times per year. And then we have to move immediately. Out of this is we have to have a lot of material in stock, but we also have to have the ability to produce customized materials. The 5 switches for Lucerne were produced within 72 hours, including delivery. And this we do with our own workforces. Going back to framework pipe installation, a little bit the requirement, most of the things are not new regarding the pipe segments. The requirement for the alignment, there we also have to take in consideration that we have minimum ±8 millimeters to respect for thermal dilatation, maybe more because of the pipe support element also have a flexibility. This is under investigation, but we have to place them very exactly, not to have a too big gap in the aluminum profile and the steel rail profile. For the pipe segment, we have decided to use the parallel running SPB line. This helps to transport the 45-ton heavy beton tubes. We will use an existing cargo wagons, which normally are used for container transportation because they have the lowest platform of the regular wagons. Loading the wagons will be done either by forklift or telescope loader. On the installation side, the goal is to use Kiro 1200. These are the biggest rail crane we have in Switzerland. A few of them are available, but they are a little bit expensive. So we have also to look to cost optimize this. As the line Golombé-Murat is a regular line used by passenger trains and from time to time also by cargo trains, we cannot easily close the line down. We are working on the best solution to get either nights or long nights or weekends that we can minimize the cost of the installation. On the other side, if we close down an operating line, we have to establish a bus substitute, which is also a cost element. What is the situation for the pipe segment placement? You see on the left the cross section. We have the power line, which will stay in place, will be shut off so we can touch it, but not damage it. This gives us a headroom above the rail of roughly 5 meters. Sounds a lot, but it's not, because the Kirov is a very big machining, and we have also to adapt a loading system, a gripper, which also takes some of the height. We have to move out of the SPB axis then the pipe segment unloaded from the cargo wagon and we have to have it placed on the pipe support elements with the necessary tolerances respected. This is the schematics. We have 3 areas during the pipe installation. On the left, production, drying and storage, and then the loading of the shuttle. We'll have a shuttle with 2 wagons. One is a protection wagon because the pipe elements are longer than our cargo wagons, and 1 wagon for the pipe segment. This will go forcing back from the loading area to the installation place, and on site is the unloading placement, and as a next activity, the repositioning of the crane for the next element. We cannot run the crane on the rail if we have the load sideways of the rail track axis. There we need to have the support legs taken in operation from the Kirov. We asked our colleagues from project management, standard operation procedure, how many pipe segments can you do in 1 hour? And the answer was 1. And we feel that's for regular construction site okay, because at the morning it's really, the line has to be open, otherwise we have 100,000 angry customers. So we looked what could be done, where is the red line, and what measurements we have to take with the goal of 5 pipe elements installed within 1 hour. We call it a little bit the aggressive scheduling. It's really using the limits. The area of loading the pipe segments on the pipe shuttle, that should be possible within 2 minutes. Load them on the wagon, but it requires pre-installation of the support element of the wagon. The pipes has really to be prepared. We have to know where the center of gravity is, so there's a lot of preparation work to be done, but loading should be possible. Pipe shuttle, I've calculated with the legal speeds, including acceleration, deceleration. We will run with max 30 kilometers per hour, but we cannot jump start and make a full stop, otherwise we have to install too much harnesses to keep the pipe segment on the wagon. Should be possible within 4 minutes. It's easy when we start, because there we have a short distance. When we are coming to the last kilometer, then it's a little bit, maybe a little bit longer, but average, if you really use all what is possible, it's should be possible. Sorry. Now the big challenge is unload the pipe segment from the shuttle, bring it to the center line of the Hyperloop, EuroTube vacuum tube axis, alpha tube axis, and then place it with the necessary accuracy. With regular crane handling, it's not possible, simply not. We have 45 tons, plus we need a loading beam to support the pipe segment at minimum 3 places. We have to turn it around. We have the external impact of wind. We have an elastic bed below the Kirov. The gravel bed is always elastic, so we have a lot of instability even with using the support legs of the Kirov. We have there not a too hard soil, and so the goal is to develop a gripper automating the handling and the alignment. So good ideas, crazy ideas are very, very welcome. With that, we should be capable, no reserves included, to reach cycle times of 12 minutes, which would give us 5 pipe segments, and if going really extreme, would mean roughly 32 hours blocked line. So within 1 weekend, actually, theoretical, the whole pipe segments could be installed. Okay. Should that mean?
Yes, thank you very much for the question, for the presentation. And now we'd like to head over to the questions. Okay, so the first question is, how many Hyperloop routes are the SPD aiming to install? What is the timeline for this? Will they always run alongside rail routes, even in the mountains?
Well, we have the lucky situation for the alpha tube that we have a railway beside. If it comes to a full scale vacuum tube transportation system, we have to go to other dimensions. It's not possible to install them parallel to existing railways. The curves are too narrow, too much G-forces would result. This would require, instead of bringing in the pipe segments by rail like we do it in the Valais, to use another system with crawlers, with whatever, or digging tunnels where you have to bring it in like it's done in power plant, hydraulic power plant system like Lindliman. So the scalable solution we develop for the alpha tube is not in respect of a diameter of something 4.5 meters and pipe segment weights of 100 tons.
Okay, then the next question, a bit related to it, it's just a more general question. Is SBB playing with the idea of running a Hyperloop system one day in the future?
Sorry, I didn't got the question.
The question is if SBB is playing with the idea of running a Hyperloop system in the future.
Well, you cannot look at national railways if you're talking about Hyperloop. Think European, think long distance, think distance 150 kilometers up to 2,000, 3,000 kilometers. And so the question, would SBB run such a system? Sure, yes, but as part of a total European system. It's really then the point to stop with national railways with speed of 900 up to 1,200 kilometers, plus the investment which has to be done, plus a total harmonization of technology, signaling, all that stuff. We cannot do this as a small country, nor even bigger European country can do this. This has to be in global. Mm-hmm. But yeah, we have an obligation to look for future solution, and we are interested to know what is going on, because one day we have to substitute aviation transportation.
Yes. Somebody wonders, where do you get all those stones for 500,000 tons ballast from?
Oh, that's a good question. We have 3 types of sleepers. And you're talking about the ballast, sorry. Ballast is 90% of Switzerland. We have several places where they do it in often the top power, open mining, but also tunnel mining. And it's transported normally by rail or even on the Vierwas Lake of Four Cantons ships, and then brought to the installation site. So majority is Switzerland, but it's in the future a problem as the permits to dig down all these stones is decreasing. And I cannot imagine that we would import ballast from India or China. Would be a nonsense.
Yes. In the beginning, you mentioned those switches and that they need to be unique. So why do all those switches need to be unique?
The history of railway was very narrow switches, narrow radius, and the system grew and grew and grew. If you look at the switch fields of Zürich Habe, this is very narrow with radius of 185 meters. Today, we will not install such radiuses anymore because it limits the speed and it forces deterioration. But it's a given thing. We cannot enlarge the whole area where we have the switches installed. So it's a history. Change is all standardizing would not work because the need of space, especially in urban areas, the need of a lot of money, and the need of time. Switches are normally 25 to 30 years in place, and so we have to live with the old geometry of the rail track system and also the diversity of the products. Beside all the switches, we have 3 different rail types with different profiles. We use 3 different sleeper systems, wood, steel, and concrete. If we change the system for replacement and we change the system, we have to go to government and ask for a Plangenehmigungsverfahren. If we just replace it one by one, we have to ask nobody. We can do this tomorrow. Asking for a regular Plangenehmigungsverfahren takes 1 to 2 years additional time to do it. So it's no way. And our answer is, and that was what we are living in Hagendorf, where we have the production site for all the switches. We have looked into how we can minimize the cost of all the different types. And as I said, every switch is unique, but we can produce them in case of emergency within a few hours. And our switches, in the meantime, are 30% less expensive than if you buy them from normal suppliers in Europe, even with Swiss labor. But we have invested a lot in automation, intelligent workforce, a single piece flow, Kanban system, and we even will have just launched another project to go there a further step ahead, and we will establish a digital supply chain and a digital production in the future. First projects are already launched, also in cooperation with ETH and EPFL.
Then somebody would like to know if the installation can also be done during snow and rain.
What's the definition of snow and rain? I would say if the wind is very strong, no, there are limitations, and that would be a nonsense. If it's icy condition, you have snow and you're in the area of plus minus 4 degrees around 0 freezing point, then we have to stop because we would collect ice on the pipe system, especially on the backside of the ice of the pipe. Normally, we have to close down when we have storm, when visibility is not anymore given in regard of security for the people on the construction site. The rain normally cannot stop us. Flood, yes.
Okay.
Is this good enough as an answer?
In my opinion, yes.
I would say in 330 days of 365 days of the year, we can work.
That sounds promising. One question is, how do you ensure tight tolerances with rail installation?
Sorry, I didn't got the question. I have some problems with hearing.
Maybe can you repeat it?
Oh. How do you ensure tight tolerances with rail installation?
Okay. That's a question we are turning around, what tolerances we actually need and how we ensure them. Goal number 1 is that the pipe segments are in a very good tolerance and very equal. Second is when we put them on the pipe support element, on the PSE elements, also the leverage, the height and the position of the PSE must be very accurate, so that we don't have to compensate with placing the pipe segments. And the rotation of the pipe segment we have to adjust. That's one of the functions we will adapt to the gripper solution. And this should lead to a solution that we can, within 5 minutes, install and align a pipe segment.
Okay, then one question is, what in your opinion is the biggest threat or risk to realize the alpha tube?
Sorry that I have to ask again.
What in your opinion is the biggest risk or threat to realize the alpha tube?
Yeah, why do you ask me? I'm just supporting EuroTube Zurich. No, I think the biggest obstacle are taken. The biggest overall risk is how everything can be financed. I see a lot of industry people, even government, who are interested that this technology is investigated, that the test installation will be put in place and can be used. I think the biggest hassle is how fast and how much money can be accumulated to install the alpha tube and run the alpha tube over a necessary period of time. The rest, I think it's a challenge, but not the risk.
Good. Then we have one question to go. How would the introduction of a Hyperloop network in Switzerland affect the rail network? Would there be fewer routes needed?
My understanding is it's an additional network system with a very few stations in Switzerland, and the regional distribution will take place more or less on the rail system how we know it today. It will replace short to medium range flying, so it will generate more passenger. Today's system is really at the limit. It could be enhanced with additional lines. My personal opinion, and I'm speaking here about myself, it's not an official meaning of SBB, we cannot use any more landscape just for mobility. And the right answer is, let's go underground, let's go in pipe tube system and establish additional system without burning more CO2, like in aviation, and without using more open landscape. So it's not a competition. And I think more than 3 to 5 stations for a Hyperloop system in Switzerland, that's really at the upper limit. We cannot accelerate the passengers with 6 G-forces and then within 4 minutes he is in Bern. That would be energetical and physical a little bit crazy.
But there will be a station in Zurich, right? There will be a station in Zurich.
Well, the stations for a Hyperloop system, a European Hyperloop system, have to be connected with the other centers of public transportation, that you have an easy switch. Well, I'm Zurich, yes. Maybe there's one in Zurich, but doesn't matter. Where you have a center of regional connection, let's go 20 meters down, and then you can hop on a long distance, 1,000 kilometer trip and go to Hamburg within 50 minutes. Then you really have an advantage. But you cannot stop then in Winterthur and Bümplitz and Schaffhausen to collect the people, because onboarding and offboarding will be a little bit time consuming in such a system. You have to take the pod out, you have to bring him back in the vacuum system. Also, you have to establish a good atmosphere in the transportation pod.
Good. Thank you very much, Jo, for sharing your inputs and this nice presentation. I hope you still hear me over the other microphone, more or less. Let me switch off this one. So thank you very much also to Oliver. It was a very great presentation showing your results from the tiling concept over the actual construction production of the tube. If anyone is interested in having the recordings or also the slides from previous presentations, please contact Natalie or me. We will compile some dossier and we'll direct them upon request. I very much enjoyed this seminar with you. We will have a continuation also in the next semester. Maybe Natalie can give us some more details about this. Yes, so thank you very much for joining. Again, I can remind you that we have open positions, so should be available if you want to be part of this adventure.
Yes. Maybe you could. Yeah. Yes, as Fabio already mentioned, we plan to continue the seminar series as of next semester, which is mid-September. For more information, please stay tuned on our website, swissloop.ch/research. And we will also post news on our social media accounts. And yes, we would be looking very forward to welcoming you again next semester. And we hope you enjoyed the seminar series as much as we did. And we hope we could offer you some insights in what is actually going on at the moment at ETH, at EuroTube, also at STB, for example, as you saw today. And as you've heard, if you're interested to do a thesis in your bachelor or master studies, feel free to reach out to Fabio or me. Or as Fabio mentioned, if you're looking for a job in these fields, feel free to reach out to him. There are always a lot of possibilities, and I think we're always up to finding really good solutions for everyone. So yes, we thank you again for being part of this new experience of walking transportation, and yes, we wish you a nice summer and hopefully see you again in September when we start again. Goodbye, everyone, and have a nice evening.
Take care.